Hello everybody, welcome to class again today. Thank you for joining me. So I just wanted to remind you that last time we were talking about, or we went over the homework for direct proofs and proof by contrapositive. And so again, we were proving theorems and we had two different techniques to do it. So today what we're going to do is we're going to move on to a new technique of proof, and that's going to be called proof by contradiction. So in a proof by contradiction, when we had the proof by contrapositive, recall that we remembered that an if-then statement, if P then Q, is equivalent to if not Q then not P. So we use these equivalent statements to say, well, if I prove equivalent statement, I get to get my original statement. And so what we're going to be doing with proof by contradiction is we're going to say that, well, recall that if not P is false, then P is true. So if we can prove that not P is false, then P must be true. So that the goal is we negate the original statement, and then we get to assume that. And what that's going to lead to is something that is clearly false. Now, in each case, that's going to be a little bit different. What is it going to be? But things like 0 is equal to 1 is a clearly false statement. And so when we run into things like that, we say, okay, that's a contradiction. Therefore, since the negation is false, the original statement has to be true. And so that's the point of a proof by contradiction. Let's go ahead and actually look at an example of that. There are no integer solutions to the equation 6x plus 15y is equal to 1. So if I look at this one, the point is I want to prove that there are no integer solutions. So in order to prove that, what I'm going to do is, by way of contradiction, is I'm going to assume that the negation of this statement is true, or that this statement is false. So we're going to assume the negation of there are no integer solutions are there are integers solutions, or there are integers such that 6x plus 15y is equal to 1. So the negation is that there exists such integers x and y such that 6x plus 15y is equal to 1. And we want to find some type of contradiction. Well, the point here is that I can do this a couple different ways, and I'll show you a couple different ways, but the idea is that somehow this is going to lead to something that has to be false. And so as I look at this, is if there are integer solutions, I get to assume x and y are integers. So if I divide both sides by, say, 3, what I get is that 2x plus 5y is equal to 1/3. So if 2x plus 5y is equal to 1/3, where x and y are integers, what this is saying is that, well, 2 times an integer is an integer, plus 5 times an integer is an integer. Hence, this side is an integer, but this side is equal to this side, so that's claiming that 1/3 is an integer. However, is 1/3 an integer? Is it a whole number? No, it is not. So, since 1/3 is not an integer, we have a contradiction. So what we had was we wanted to show that there were no integer solutions, so we assumed that there were integer solutions. And then if there were integer solutions, that would imply that 1/3 would have to be an integer. But since we know 1/3 is not an integer by definition, we get a contradiction. Hence, the negation has to be false, so the original has to be true. All right. And I was saying there was multiple ways to do this. If you want it to work with Mongeau arithmetic, notice that since these are equal, 1 is congruent to 6x plus 15y mod 3, we could say. But this is congruent to, 6 is congruent to 0 times x plus 0 times y mod 3, which is 0 times any integer is 0, plus 0 times an integer is 0. So we get 0 mod 5. And the reason why I wanted to do this one is because what we're saying here is that 1 is congruent to 0, 1 mod 5. So that is 1 is equal to 0. since 1 is not equal to 0, even mod 5, that implies that we have a contradiction, so therefore the original statement is false. So there's two distinct ways, but the point here is that we get that there can't be any integer solutions, because I could divide this, if there were, I could divide this side, and I'd still get an integer when I divide by 3, but this side, when divided by 3, is not an integer, so that cannot be the case. All right. If you guys have any questions, just chime in whenever you want. The next thing I want to do is I want to show that if A and B are Z, if 2 divides A times B, then 2 divides A or 2 divides B. This one's a lemma because I need it for my next proof by contradiction. So I'm actually just going to prove this one actually by contrapositive. And so if I do the contrapositive, my assumption is going to be assume that 2 does not divide A and 2 does not divide B. So the negation of an or is an and. I negate both statements because I'm negating the then. So instead of 2 divides A or 2 divides B, we get 2 does not divide A or 2 does not divide B. And what we have to show is that 2 does not divide A times B. Now, what I want to point out here is, okay, well, if I'm using this, if 2 does not divide A, I do want to point out that, remember that if 2 divides A, we're even. So if 2 does not divide A, we're odd. An equivalent way to say that we're odd is to say that A is congruent to 1 mod 2. And this is saying that B is equivalent to 1 mod 2. And again, I'm going to use mods here because it's going to save me some algebraic manipulations. But the idea is that, okay, 2 does not divide it, therefore it's not even, therefore it must be odd. We could also write A as 2k1 plus 1, B as 2k2 plus 1, and we can use that somehow algebraically, but I think this one will work out nicely. If I continue with that, I have to show 2 does not divide A times B, so that means I also have to show that A times B is congruent to 1 mod 2. All right, with that said, if I have to show A times B is congruent to 1 mod 2, notice that I can do a substitution because mods respect multiplication. So A is congruent to 1, so I can just put in 1. B is congruent to 1, so I can put in 1. So I get A times B is congruent to 1 times 1 mod 2, which is, well, 1 times 1 is just 1, so I get 1 mod 2. Hence, A times B is congruent to 1 mod 2. Hence, 2 does not divide AB. Now, so here's my proof, and that follows. So if I multiply two odd numbers, basically what I'm saying is I get an odd number. So if I have an even number, if I go back to the original statement, if I have an even number that's written as A times B, that means that either A is even or B is even. Both could also be even, but at least one of them has to be even, because in the case that I multiply two odds, I again get an odd. So I can never multiply two odds and get out an even, is really what this lemma is saying. All right. Now, I said that that was a lemma because I'm going to use it for my next theorem. And the next theorem is actually a pretty exciting one. I see I have a question here, so let me address that before moving on. So the difference between a contradiction and a contrapositive, remember that a contrapositive was if we're trying to prove if P then Q, what we show instead is if not Q then not P. So we're not contradicting this, we're not assuming this is false, we're actually just proving something that is logically equivalent. Whereas with the contradiction, we just have a statement like P, and then what we do is we assume not P, and we show not P is false. Now, when do you use one or the other? Well, if I have an if, then I can use a contradiction, and this would be the contradiction or the negation of if P then Q is P and not Q. So we could assume P and not Q and find a contradiction, and that's fine. But the distinction here is just that here I have a theorem I'm trying to prove. Instead of trying to prove something that's equivalent to it, I find the negation or the opposite, and I show the opposite has to be false. Because the negation is false, the original has to be true. Whereas here, I just switch the order of the if then and negate each statement. So I'm doing negations, but of each portion, but the entire thing is still equivalent to the original. So I want to get a true here, whereas here I want to get a false. Is that clear enough, Andrea? All right, good. So now here, what I'm going to have is first off, I wanted to remind us that a rational number is any number that can be written in the form of an integer divided by an integer where the bottom is non-zero. And what I want to do is I want to show that the square root of 2 is not rational. And I'm going to need that previous lemma for that. So somehow I'm going to have to show that this is true. So let's go ahead and walk through that. All right. So if I wanted to say the square root of 2 is not rational, the idea would be to show that it's not rational means that for any a and b, any integers a and b, if I write a over b, I will never get the square root of 2. So if I wanted to try to prove this one directly, as far as what we have been doing, a direct proof or even a contrapositive is, well, I'd have to set this up and I'd have to say, well, there is no way that or if I take any a and b, a over b will never be the square root of 2 for any integers a and b. And so actually to prove this, I'd have to check every integer a, divide by every integer b, and make sure that that's never equal to that. And so this is actually a very complicated proof because, well, there are infinitely many integers, so there are infinitely many things I'd have to check to show that this isn't the case. This is really the power here in the proof by contradiction is instead of assuming that this is not rational, what I can assume is the square root of 2 is rational. Then what I get is I don't have to work with all integers. I just have to say then the square root of 2 is equal to a divided by b for some integers a and b with b not equal to 0. So the point here is instead of having to work with all integers, I can just say that there exists an a and b. And so I can look at a, I can look at b, and I can explicitly say that square root of 2 is this a divided by this b. So I only have to work with one number as opposed to having to check every single number. And so the goal here is, okay, if I assume that it is rational, somehow I need to get out a contradiction. So somehow from assuming this, I need a contradiction. Well, how do I do that? Well, the first thing I want to notice is I'm just going to look at the square root of 2 is a over b. I need some more room, so let's focus on that. What I can do here is, since the square root of 2 is equal to a over b, I can square both sides, and I should get 2 is a over b squared. Which means that 2 is a squared over b squared. So 2b squared is equal to a squared. Is that helpful at all? I don't know. It was just some random stuff I thought to do. Trying things, seeing if that works. Well, what this tells me, and what I can see from this, is that 2 times b squared is a squared, so therefore 2 divides a squared. So what does that mean? Well, that means that a squared is even. All right. How is that helpful? Well, remember that in our theorem we showed that if 2 divides a times b, then 2 divides a or 2 divides b, or rather our lemma. But now in this case what we get is 2 divides a times a, so 2 divides a or 2 divides a. So by our lemma, what we have is that 2 divides a. So that's why we needed this here, is because we have the product here, a times a. We know then that since 2 divides the product, it has to divide one of the terms. Since both terms are a, that means that 2 has to divide a. Therefore, a is an even number. So the only way that the square root of 2 can be a over b is if a is even. All right. Well, let's work with that. If a is even, let's say it's equal to 2k for some integer k. Then if I look at this, I had 2b squared is a squared. So 2b squared is 2k squared. So I get 2b squared is, and if I square this out, I get 4k squared. But now I can divide both sides by 2, and I get b squared is 2k squared. So what I get is that, well, for the same reason, 2 divides b squared, because 2 times an integer is b squared. Hence, 2 divides b by our lemma, because 2 divides b times b, so 2 divides b. All right. Let's say, so 2 is, our b is 2 times some other integer we'll call k1 here, just to call it something different. Now, here's kind of the trickier part is, notice that I said that square root of 2 was a over b, but I just claimed that a was even and b was even. So what can I do here is, if this was an actual rational number and I had an even over an even, I could, well, cancel out the 2's and I get k over k1. So therefore, the square root of 2 would have to be a over b. Well, a would have to be even and b would have to be even, so therefore the square root of 2 would also have to be k over k1. But square root of 2 is equal to this, so what does that mean? Well, it means that both of these are even, right? So I get 2 times, I need a new letter now. Let's just say, I think I'm up to k2 over k3. These would both have to be even by the same proof we just did, so we can cancel out a 2 again. And we can keep doing this, and we can keep canceling out 2's forever. So I can cancel out infinitely many 2's, but what does that mean is that a is equal to infinitely many 2's, let's say 2 to the infinity times some integer, and b is equal to 2 to the infinity times some integer. So if I can factor out 2 an infinite number of times, what does that mean about a or b? Well, technically, if a was 0, I could keep factoring out 2 infinitely many times, because 0 divided by 2 is just 0, 0, 0, 0, 0, and there isn't a contradiction there. But I know b is non-zero, and that's the important part, because if it was 0, I'm dividing by 0, so that's not a rational number. So here I have a non-zero number. I keep factoring out 2. I can do that infinitely many times. So that would imply that b is an infinite number, which contradicts the fact that it was an integer, because any integer is finite and therefore not infinite. So therefore we get a contradiction, because b is not infinite or 0. So what's the point here is that, well, if the square root of 2 was irrational, then both the top and bottom would have to be even, but then we could factor out, and we can do this indefinitely many times, which leads to a contradiction, because if each of these are finite numbers, we can only factor out 2 a limited number of times. So there's our contradiction. What does that mean? Well, that means that the square root of 2 is not rational, which, why is that so amazing, is because we've talked about rational numbers, which was the set Q, and I mentioned that there are real numbers that are not rational or are not Q, but we've never actually proven that there's anything in this set. So what have we just done is we've come up with an example of something that is in the set R not Q. That is, we've found a real number that is not rational. So we've shown that the real numbers and the rational numbers are not the same set. There are things distinctly in the irrationals that are not in the rationals, which, while it's something we may have talked about, we now have a formal proof that that is true. And so we have to actually face the fact that, yes, there are irrational numbers. All right. So, you don't understand why it's a contradiction that b can't be infinite. So let's actually look at that. The idea here is that b has to be a finite number. So b is something like, I don't know, 1 million. There. Now, it could be some huge number. It can be even bigger. But the idea is that if I divide b by 2, what I get is this is going to be half as big. And if I divide that number by 2, so I'm just going to say that number by 2, I get something half as big. Notice that each time I'm getting smaller, right? So, each time I'm going to get smaller, but I also want to point out that if this is positive, I'm going to stay positive. So each time I'm going to get smaller, but I'm going to stay positive. And I'm going to get smaller and smaller and smaller and smaller. Now, eventually, if I get small enough, if I keep dividing by 2, I'm going to end up with somewhere where this is, well, if it's an odd number, that's enough, but eventually it has to be 1, for example. And if I divide by 2 again, I get, say, 1/2. So whenever I run into that odd number, whatever it happens to be, what I've just said is that I should still be able to divide by 2. But if I look at this, the point is that this, each time I divide by 2, has to be an integer. So if I keep dividing by 2, eventually I'm going to end up with something that's not an integer. And to show that, what you could really say is, notice, this is going to be smaller than this is smaller than this. So even if we worked our way down, there could be 1 million integers here when I'm dividing by 2. I could do this a million times, but the million and first time, the biggest I could be is 1. Therefore, the next time I divide by 2, I have to get a fraction, which is not an integer. If this was 10 billion, I could supposedly divide by 2 10 billion times, but eventually I have to be less than or equal to 1. Therefore, the next time I divide by 2, I'll have to be a fraction. I can't be an integer. So the fact that these have to be integers and they can't be when I divide by 2 enough times, that's the contradiction. Does that help out? All right. And Ninja, the invite to Discord is on Blackboard on the announcements. So log in there and you can log in that way. All right. I just don't have the invite on hand, so I'm going to refer you there because that'll be the easiest way to get that. Now, I just want to point out that the fact that the square root of 2 is irrational is actually one of the proofs by contradictions that everybody does. It's one of the things that shows the utility of contradiction. It is that proof that works out so well. Without it, there really isn't a nice way to show that the square root of 2 is irrational. So we really always, whenever we show that is, we work with a proof by contradiction in the same way. And it comes up enough that in your homework you have things like prove that the cube root of 2 is irrational, or prove the square root of 3 is irrational, and a lot of it's going to work through in a very similar manner. And so you can use that proof and kind of generalize to work with different cases. And you'll notice that when you take the square root of any non-perfect square integer, you're going to end up with an irrational number. And so it is a very beautiful proof because it does give us such a wonderful result in a way that originally that looked like it would just be impossible to prove. All right. The next, or the other major proof by contradiction, is that there are infinitely many primes. So actually the proof we're going to be doing today follows the proof that was done by Euclid in, no, I'm blanking on this, in the Elements. There we go. So Euclid's proof in the Elements that there are infinitely many primes. So that was over 2,000 years ago that was written, and we're still using exactly the same proof today. Well, I mean up to some type of notation changes, but essentially the same proof. So just as a heads up, as we get to this, this is over 2,000-year-old proof, and I think that's really amazing. It is amazing that something can hold up that well for so long. And that is the point of mathematics, is that once you've proven something, it's always going to be true. So even though the proof's 2,000 years old, it still holds up. And it's just, there's no other area of expertise where things like that happen, where a proof is given and it's true forever. So many things get replaced by a better understanding of what's going on later on, that having that type of consistency and this ever-holding proof, that's just a really wonderful thing in my mind. All right, so what is this proof going to look like? Let's actually go ahead and do that. So yes, Andre, we essentially, or on that, we do deliberately create a false statement, and we prove that it's false. So therefore, the negation of that statement has to be true. That is the entire point of proof by contradiction. So we write down something that has to be false, and then we show it has to be false so that the original had to be true, or the negation of the false statement had to be true. All right, so if we want to show there are infinitely many primes, just a little story. If we wanted to show that there were infinitely many primes, what would we have to do is we'd actually have to construct infinitely many primes. So we could say 2 is prime, then 3 is prime, then 5 is prime, and we'd have to actually say how to keep finding primes forever. And so I'd have to be able to find all primes going on and on and on to show that this is an infinite set. So that's what a direct proof would look like. Now, I want to point out that this was proven 2,000 years ago, but this still hasn't been done. One of the big things about the Riemann hypothesis is that it gave us a way to at least find where prime numbers would be, and so it would show us how we could, in theory, construct infinitely many prime numbers. And that is, if you could prove the Riemann hypothesis, you could get a direct proof that there are infinitely many primes. And the reason why I'm bringing that up is that was one of those millennial challenges, and I think 2 years ago now, someone came out and said they have a proof of it. Michael Ataya, he died afterwards, and so I think we're still looking at the proof. I haven't seen it, so I don't know if it's correct or not. We haven't really decided as a community if it's correct or not. But the point is, it's something that's still an ongoing area of study in mathematics. It's something that's still interesting. Even if his proof is incorrect, that just means there's more work to do. Or if it is correct, well then that's really exciting because we've done something that we've been trying to do for thousands of years. All right. going back to this one, just 3 answers. Someone was asking for the Discord invite again. Remember, that is on Blackboard. I'm trying not to share it publicly because I had troubles in one of my classes where people were logging in and doing stuff that was not appropriate. So please go to Blackboard, and on their announcements you can find the invite to the Discord. I don't think anybody is talking in Discord anyway. Alright, where were we? We're trying to show that there are infinitely many primes. So if we want to do this by proof by contradiction, we're going to assume that there are finitely many primes. Alright, I don't know where this contradiction is going to come from, but somewhere along the way we're going to end up assuming something, and we're going to get something that's going to happen that can't be the case. So what are we going to do is, well, the first thing we notice, since there are finitely many primes, I'm just going to let P be the set of all primes. Let's say P1 through P2 all the way out to P sub k. Now, I don't know how many there are going to be. There can be a lot of them. But the point is that since there are finitely many of them, I can list them, and there's going to be k of them. So I can say there's exactly k of them, whatever that happens to be. So these are all of the primes. I've listed them all out, and I can do that because there are only finitely many. What our goal is going to be is it's going to be to take this and show something that contradicts this. And in particular, what we're going to want to do is say, well, if these are all prime, can we find another number that is bigger than all of these that must also be prime? So that is, if we can find a number p sub k plus 1 that's bigger than all of these, since it's bigger than all of these, it can't be in the set. If it's also prime, then we're showing that there is another prime that's not in the set of all primes. So that's a contradiction because this has to be all primes. So that's where we're going. Well, how are we going to do that is, the first thing I wanted to say is note that A divides N if and only if A is congruent, or N is, sorry, let's say N divides A if and only if A is congruent to 0 mod N. So I like to do mod N here. So N divides A if and only if A is congruent to 0 mod N. And we actually did prove that is by our definition. Remember, we said that N divides B, or A is congruent to B mod N if and only if N divides B minus A. Well, if we take 0 minus A, we get negative A. Well, if negative A is divisible by N, then A is divisible by N, because we can multiply by the negative of it. And so if we go this direction, we get the same thing out. And so we do actually have this from our previous theorem. And so if we can show that our number is not congruent to 0 mod N, then we show that it's not divisible by these numbers. And so we're going to have to use this as we go forward. All right. With that in mind, what I'm going to do is I'm going to let's say A equal P1 times P2 out to PK plus 1. So that is, I'm going to find a number A, and I'm going to say that I'm going to find it just by multiplying all of these primes together, and then I'm going to add 1. So if I multiply all these primes together and add 1, what I want to point out is, what is A mod P sub I congruent to for any of the primes? Well, notice that P sub I divides this term. So this term is going to be, instead of P sub I, I get 0 times a bunch of integers in mod arithmetic. So if I take 0 times a bunch of integers, I get 0 plus 1. So for all of these numbers, all of these primes, A is congruent to 1 mod P sub I. What does that mean? Well, since A is divisible by the p sub I if and only if it's congruent to 0 mod p sub I, that means that A is not divisible by any prime number. Now, since A is not divisible by any prime number, that means that, well, it's not divisible by any products of primes, and therefore, I can't write this as a product of two numbers that are smaller than it, because if I could write this as a product of numbers that are smaller than it, I could then rewrite those as a product of numbers smaller than it, or their primes, which would contradict here, and so I'd have to be able to keep factoring where I never get out any primes, which again would mean that this is an infinite number. So the point here is that if I'm able to factor a number at all, eventually I'm going to factor it into a product of primes. Since I can't divide this by any primes, I can't write it as the product of primes. Therefore, A is prime. That is, I can't write it as the product of any numbers other than 1 in itself, so therefore it has to be prime because I can't write it as the product of prime numbers. But because it's the product of these, notice that each of these is greater than or equal to 1, or greater than or equal to 2 actually, so the product is going to be bigger than all of these. And then I'm adding 1, so I'm bigger than all of these. Hence, this will be a prime number, which is not in this set. And so what I'm saying here is that A is prime, but also A is not prime. Hence, we have a contradiction. Therefore, we get that A is both prime and not prime, so that can't be the case. Therefore, if we had a finite set of primes, well, that can't be the case because we could always find another one. Hence, there has to be infinitely many primes. And so there will indeed be infinitely many primes. Does that make sense to everybody? All right, start over from the let A part. So the A, what I'm going to do is I just want to define it so that I know it ends up being prime. And I know that this is going to be prime if it's not divisible by any prime number. So I'm trying to find a number that is not divisible by any prime. So what I did is I multiplied all the primes together to get something that this is divisible by every single prime. So if I want something not divisible by any of those primes, I can just add 1 to it. Since that would imply that this is congruent to 1 mod all of my primes, and all of my primes are greater than or equal to 2, 1 is not congruent to 0, so therefore I took this number is divisible by all of the primes, so I added 1, I ended up with a number which is not divisible by any prime. Therefore, if it's not divisible by any prime, that implies that A is prime. Since A is prime, and it's not an element of the prime numbers, it is both prime and not prime, and that's my contradiction. Is 1 prime? 1 is not prime, actually. So a prime number that is a number other than, or for the prime natural number, is a number other than 1, which is divisible only by itself in 1. The reason why we exclude 1 is because if you look at a generalized version of prime in numbers other than the natural numbers, a prime number is defined as a number p such that if it divides a times b, then p divides a or p divides b, and p is a non-zero non-unit. All right, and this is the point that we're talking about. Why do we exclude 1? Is because we want to exclude any 0 number, but we also want to exclude units. What's a unit? A unit is a number that divides every other number in the set. Since 1 divides everything, it's a unit. Therefore, we're going to exclude units, we're going to exclude zeros. So if we're talking about primes, we exclude 1. All right, so does that mean the original statement is true? Yes, Sammy. So we showed that there can't be finitely many primes. Therefore, there has to be infinitely many primes. So our original statement that there are infinitely many primes is indeed true. That's what we have just proven. That is exactly correct. All right. Any other questions then about proof by contradictions? All right. I don't see any other questions about proof by contradiction. I know that we still have a half hour left in class, but as I said, since we're doing these working from home things, I'm not actually going to push us too hard. So I'm going to actually just leave it there. Those are our proofs by contradictions. I would suggest starting to look at the homework that will be due on Tuesday, which will be out of the chapter from proof by contradiction. I'll post that shortly here so that you guys can get into that. But otherwise, I hope you have a wonderful day, and I will see you on Tuesday.